This is part 3 of stereochemistry, and we'll conclude stereochemistry by looking at cycloalkanes, types of strain energy, and also axial and equatorial bonds. So in this session, we'll look at cycloalkane conformations. We'll learn the angle, the torsional and strain, steric strain. Then we also must how to draw the shear conformations and also distinguish axial from equatorial bonds. Then we'll look at how to solve some questions. So let's start with cyclohexane. Okay, we can start with cycloalkanes. So for cycloalkanes, they're just alkanes that have carbons which can form a ring. So we are saying these are alkanes that have carbon atoms rather, that form a ring. Those are what are known as cycloalkanes. So we are saying they are just simple alkanes. Yeah, they are just simple ring of this bond, which is just CH2 bonds like that. And you know that the formula, it is CH2 then with an N, so it is this kind of a structure. Alright, so let's look at some of these cycloalkanes. We can look at cyclopropane. So cyclopropane, since propane is a 3, has 3 carbons rather, like that. So we have that carbon there, that carbon there, that carbon, then they will bond to form a ring like that. Then we call it cyclopropane. So the structure for cyclopropane is just that structure. Then when we talk of cyclobutane, so we are simply talking about butane forming a structure like that with 4 carbons. This has 4 carbons, propane has 3 carbons. So that is cyclobutane. Then when you're talking about cyclopentane, we are just talking about a structure which can be formed in that manner. So this is cyclopentane with how many carbons? 5. Then when you're talking about cyclohexane is just the structure with 6 carbons. So this one has 6 carbons, so that is cyclohexane. Then we can also look at this same propane rather. So what if they want us to draw, let's say, a Newman projection for this cyclopropane? So Newman projection. So the Newman projection, we can get it from the model, like the way the model for cyclopropane is, it looks like this. Then it has small bonds like that for these small hydrogens, like that. Like that, like that. Then even there also have the bond there. So this is the model. So in converting into a Newman projection, we'll say our first carbon here, so simply have this. Then to have the second carbon, then we can attach this first carbon to another carbon this side. So we'll have a hydrogen there, hydrogen. Then we can also have these hydrogens at the back. Then this side also we can do like this. Since it is cyclic, meaning that even the back carbon will be attached to this third carbon, then we can have the two hydrogens like that. So this is how you draw the cyclopropane in a Newman projection. And we should know that molecules, when they are equipped into another molecules, they are made to be active. Okay, so that is what we need to understand from there. Then let's look at cis and trans conformers. Or cis and trans isomers for this cyclopropane. So you can have the cyclopropane like that, then both bulk groups like this methyl facing on top like that, even this side. Then we can have the hydrogens down like that, so meaning that this is cis, and we'll name it. Then we can have the same kind of structure, but for this one have this methyl in adjacent allocations like that. So this is cyclopropane and this is cyclopropane, but there's a difference. This is cis. You can see that the methyl groups are on top, so this we call it cis, and you can name this one as carbon number 1, carbon number 2, so it is cis 1, 2, and there we have dimethyl cyclopropane. Then for this other one, we can see that it is 1, 2, so both, it also has carbon number 1, we have a methyl, carbon number 2, we have a methyl, but the difference is that this one is trans. So this is trans 1, 2 dimethyl cyclopropane, like that. That is what we need to understand there. Then when it comes to stability of this cycloalkanes, we can be asked to calculate the angle of stability. So let's say we have a structure like this, then we have the angle which is here to be 49 degrees. So they can ask us to calculate what is the angle of stability. Calculate the angle of stability. So the angle of stability is simply this angle, which is here. So you can see that here we have a 49, and inside here we have a triangle which is equilateral, has 60 degrees as in triangles. So you can say angle of stability will be equal to 49 degrees plus the angle which is inside, which is at 60 degrees, and we'll get a 106 degrees. So that is our angle of stability. Then if we have a structure in this manner, which is a cyclobutane, our angle of stability, so this is our reference point. This angle is one we are looking for. So let's say we have a 19 here. So we'll be given this, then we'll be given this value, then we will be told to calculate the angle of stability. So the angle of stability will be equal to 19 degrees plus a 90 degree, and this will be, this is 9, this is 10, so it will be 109 degrees. So this will be our value, which is 109 degrees. Now the next thing we'll look at is what is known as a Bayer theory, a Bayer strain theory. So a Bayer strain theory, it is just a theory which was proposed in 1885, and you know that since carbon prefers to have bond angles approximately around 109 degrees, so the ring size, which are other than 5 and 6, may be 2 strains to be in existence. So that is one thing we must know. So under this theory, we are saying that carbon prefers angles of approximately 109 degrees, and ring size other than 5 and 6 maybe 2 strains to be in existence. So that is one thing we must understand about this theory. Okay, so let's now look at let's look at types of strain. So we have 3 major types of strain. There is what is known as angle strain. When you're talking about angle strain, it is just the expansion and the compression of the angle bond away from the more stable. So here we're just talking about compressions, expansions, and compressions away from the most stable angle, which we said 109.5 degrees. Okay, away from 109.5 degrees. So that is what we call angle strain. Then when you're talking about steric strain, as we discussed in the previous session, we said it is just that repulsive interaction between non-bonded atoms in close proximity. So it is just that that repulsive interaction. For example, if the hydrogens are close to each other, there will be that repulsion. Okay, because they are too close to each other, that is steric strain. Then when you're talking about ring strain, ring strain is about the combination of angle strain and torsional strain. So ring strain, it is angle strain plus the torsional strain. And you know that torsional strain, it is just that resistance of an atom from being twisted. Okay, that is torsional strain, like the force which exists due to that resistance from it being rotated. That is the torsional strain. So in simple terms, you can say it is just the crimping of bonds of neighboring atoms. So that is what we simply mean by torsional strain. Now let's look at another structure for cyclobutane. So how do you draw it in Newman projection? So we can start with this. Okay, like that. So we have a carbon in front and the carbon in behind, the carbon behind. So we have a hydrogen there, a hydrogen, then we have another hydrogen like that. Then we're going to have this carbon here, okay, bonded to the first carbon there. Then we're going to have another carbon, because cyclobutane should have 4 carbons, so you can have another carbon here, then you can have another carbon here. Then this other carbon will be bonded, because it's forming a ring, so it should be bonded behind that other carbon. Then we must put the hydrogen now, like that, and like that. So that is our cyclobutane. So we just draw the first 2 carbons, then the first one should be connected to 2 carbons here. So there is a carbon, okay, like that. Then it should be bonded again to another carbon, then it should form something like a ring. Then the 4th carbon should be bonded to now this structure here, this carbon which is behind. So that is how you come up with the structure. Let's count the carbons. 1, 2, 3, 4. Oh, sorry, there shouldn't be any bond here. Cyclobutane should have just 4 bonds. So just like that. So this is cyclobutane. So that's how you come up with a Newman projection. This is a Newman projection for cyclobutane. Then when you're looking at cyclopentane, the Newman projection, we can start with the bond here. So we have a hydrogen and another hydrogen. Then we have a back carbon there bonded to a hydrogen. Then we can have that carbon there with two hydrogens like that. Then we have that carbon. Since there are 5, they are forming a ring. We must have another carbon there. Then there will be that ring formation. Then with a hydrogen there, a hydrogen there, a hydrogen, and here a hydrogen. So you can count the number of carbon atoms: 1, 2, 3, 4, and 5. So this is cyclopentane, and we have drawn it in a Newman projection. So that is how you draw the structure. Now let's look at how about, okay, so I should mention one thing here, that when you have cyclopentane, one carbon, which is this carbon, is packed. So one carbon is packed. So it is due to this packaging that the fifth carbon will appear to be below or above. So it will appear to be below. This carbon might appear to be below or above due to that packaging. Okay. Then one thing is that this actual conformation of cyclopentane is non-planar, hence reducing the torsional strain. So we should also consider that. Then let's look at now cyclohexane. So for cyclohexane, you start with the parallel lines like that. Then the longer one should go like that. Then this side also must have that. Then we can put, so axial, it is on top. So here, let me even introduce axial and equatorial bond. So for axial and equatorial, okay, so for axial, the hydrogen there, it is in axial, meaning that it should be upward like that. Then when it is equatorial, it must be slanting. And one thing we need to understand about equatorial and axial is that equatorial have high strength or high stability than axial. So we need to understand that. So that is axial. Then equatorial now must be this bond. So equatorial will be that bond. Okay, so this should be, okay, so axial. Then we have equatorial. Let's start with writing those which are in axial. So axial hydrogen, even there, axial hydrogen, even there. So it should face down here. Axial, and there axial. Then I'll use a different ink to indicate those in equatorial. So here, okay, so here to go like that, slanting towards this line, so have equatorial like that. Okay, then they must be facing each other like that. Equatorial like that. Then at this point also equatorial like that. Then there we have equatorial. There we have equatorial. So this is how we come up with the cyclohexane. So this is where we end. Thank you for watching. Don't forget to subscribe.